The study of what makes life tick is the most exciting and dramatic adventure as a scientist or as a human being that I can imagine. Hi, I'm Cliff Brangwynne, a professor at Princeton University, and I work in bioengineering. Bioengineering is work that's at the interface of the life sciences and engineering. In some manifestations, it's been around for a few years, but it is still very early, somewhere where computers were in the early 1970s. At that stage, there was no internet, there was no Google, there was no Amazon. We're going to see incredible transformative impact over the coming decades. Cells are incredibly complex. Any point inside of a cell, anything one can look at, you could spend a lifetime studying it. That's how complex it is. It requires incredible dedication to understand even a sub-component of a cell. And in fact, living systems are the most complicated forms of matter in the universe. The way in which they're delicately arranged, the processes at play are unlike anything in the non-living universe. They're more richly structured, more richly textured. The principles by which they're held together and they operate are not understood. Yeah, it's the most fascinating aspect of the natural world. My colleagues and I have discovered that a class of structures within living cells are organized according to physical principles that are also at play in the non-living world. We refer to these structures as condensates, intracellular or biomolecular condensates. They reflect the condensation into liquid-like droplets of biomolecules within living cells. This is the same physical driving force that causes water molecules to condense into raindrops. That same fundamental physics is also at play within living cells, and those liquid droplets are at the heart of many physiological processes that all of our cells are undergoing right now, controlling biochemical reactions within our cells. And these structures are also at the heart of many diseases like cancer, ALS, and Alzheimer's. One of the hopes is that one can use these principles to target the process by which condensates form to alter the behavior of cells. For example, cancer cells are growing uncontrollably because there are condensates within their nucleus that are telling a cell, grow, 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 grow. And so we're now thinking about ways to target those structures to stop a cancer cell from growing or to stop a neuron from dying because its condensates are not operating properly. I can see a world in which living systems are able to be changed and manipulated for human health and society benefits in the same way that we manipulate non-living matter. Control systems, lenses for optics, harnessing electromagnetic radiation for communications and so forth. I can look into the future and see a world in which living systems are manipulated with just as much control so that we can make completely new kinds of materials based on biological organisms. Biological matter is qualitatively different. It's the most complex form of matter in the universe, but if we can manipulate it, which is on the horizon, the opportunities for improving human health and society are limitless. I'm Cliff Brangwynne, and I'm a forward thinker.